Thank you. Okay, so let me jump into the middle without further ado. So I'm talking about the graph isomorphism problem. Oops, and I guess, yeah. So the input is that I have two graphs with n vertices. The question is, are they isomorphic? Here is an illustration of two graphs that are isomorphic, but it's not immediately clear. The trivial bound, of course, is essentially n factorial. I mean, you try all bijections. A highly non-trivial bound was obtained in 1983 after a sequence of major developments over a course of about 4 years preceding that. And then the general case stalled at that, and so in this paper I'm claiming that one can do it in quasi-polynomial time exponential in polylog. Okay, so it involves group theory ever since 1979. The method of choice has been group theory and in combination with combinatorial algorithms. So let me tell you about a result that is at the heart of the new algorithm. So first of all, we are going to look at permutation groups. So omega is a finite set, and we look at a subgroup of the symmetric group over that domain. That's called a permutation group acting on omega, and omega will always have n elements. The stabilizer of an element of this permutation domain, this is denoted by G sub x, and that consists of all permutations from that group that fix x. So this is the subgroup of, consisting of the elements that fix x. And now here comes the definition that suppose we have a homomorphism of G onto an alternating group on some other domain. So that other domain I denote by gamma, and gamma is always going to have m elements, and these two parameters n and m are going to be central to this entire algorithm. And so the definition is this: an element of the domain is affected by this epimorphism phi if the image of the stabilizer under this epimorphism is not all of the alternating group, okay? So the stabilizer is a subgroup of G. It could still happen that it maps onto this alternating group. Then I say that that point x is not affected, and otherwise it is affected, okay? I could quote Moby Dick for this definition. And yeah, so that was about the definition of what's a whale. And then here is the result. Here is the central group theory result which is at the heart of the entire algorithm, and I call that the unaffected stabilizer lemma. So if we look at the set U of all unaffected elements of omega, okay? So those for which the stabilizer still maps onto the entire alternating group on gamma, I look at the pointwise stabilizer of this set. So G sub parenthesis U denotes the pointwise stabilizer of that set. So it is the intersection of the stabilizers of all unaffected points. And if m is not too small, well, never mind this number 8, but if it is greater than 2 plus base 2 logarithm of n, then even the intersection of these stabilizers still maps onto the entire alternating group. Okay, so that is the result. Okay, so let me illustrate it. So here is the group G. Here is the alternating group of degree m onto which it maps. Here is the stabilizer, that's a subgroup. And that subgroup can well still map. This is the situation when x is unaffected. And let's look at a few unaffected points. Let's look at all of them. Then their stabilizers intersect in the pointwise stabilizer of all unaffected points. And even that will then map onto the alternating group. So this should already smell a little bit counterintuitive, but let me mention, well, an obvious corollary to this is that at least one point is affected. Now, why? This is just a test if everybody is still awake. Yeah? Not the empty set, the one-element set. Yeah, yes, right. If no point was affected, then that would mean that this set here consists of the identity only, and that, of course, cannot map onto a substantial size alternating group, okay? Now, this result is tight. So if I replace greater than by greater than or equal, then there are infinitely many cases where there is no affected point at all. Okay? Another thing I'd like to mention about this is that I forgot to write here, that currently the proof of this is based on the classification of finite simple groups through a simply stated consequence, namely Schreyer's hypothesis, which says that the outer automorphism group of every finite simple group is solvable. So that's being used in the proof of this result. But it is more interesting, and maybe tomorrow I'm going to give the examples, very simply constructed examples that show that this bound is as tight as it gets. Okay? And then, of course, the question is how on earth is this result related to the graph isomorphism problem? And I don't think today I will be able to connect all the dots, not even tomorrow, but I am doing my best. Okay? So that's the job here. So first of all, I'd like to define a more general problem. That problem is what I'm going to address. And this is the string isomorphism problem. So if we have a string and we have a permutation, then we can apply that permutation to the string, and then we get another permutation. Okay, this was invented for the purposes of talking Boston. So, okay, so omega is going to be the set of positions, and a string is simply a map from the set of positions to some finite alphabet, and then a permutation x by scrambling the letters. So basically, yeah, so this is the basically we are talking about anagrams, but anagrams where the permutation of the positions is restricted to a particular given group. And then I say that two strings are isomorphic under the action of this group if there is an element in the group that transforms one of them into the other, and the string isomorphism problem is to decide whether or not this is the case, given three pieces of input. One is the permutation group and two strings. Okay? That problem was defined by Lux in his seminal paper in 1980, well, 80 or 82, depending on whether you look at the conference version or the journal version. And Jean Lux made also immediately profound applications of that to the graph isomorphism problem. Another way of looking at it, if you want to popularize this in class, is that imagine that you have two Rubik's cubes, and you color the faces not in the usual way, but completely arbitrarily. Okay, so you just attach little colored squares everywhere. Maybe you use only two colors. And then you want to find out whether or not a given coloring can be transformed by legal moves of Rubik's Cube into another. Okay? So this also illustrates a question that you should be shouting already by now. How do we represent a permutation group? Permutation groups are exponentially large compared to the size of the domain. So what would be a reasonable representation for the purposes of complexity? Yeah, a list of generators. And of course, every permutation group of degree n has a list of, in fact, every minimal set of generators of permutation group of degree n is not more than 2n elements. So a linear number of permutations actually is sufficient. And so that's when I say that a group is given, I always mean that the group is given by a list of generators. Okay? All right. So the string isomorphism problem has also been considered, and also in the old days, the previous best estimate was my paper from 1983, which was also exponential in roughly square root of n. The tilde hides a polylogarithmic term there, and now my claim is that string isomorphism is decidable in quasi-polynomial time. Okay, so the first thing I have to argue that graph isomorphism reduces to this problem. This was pointed out by Jean Lux. Well, graphs, these n vertices can be encoded by 0, 1 streaks of length n choose 2 in an obvious manner. And then, if we look at the induced action of the symmetric group of degree n on the set of pairs, of the set of n choose 2 pairs, like look at the complete graph on n vertices, then the symmetric group that permutes the vertices also permutes the n choose 2 edges. Okay? And these edges are labeled 0 and 1 to define a graph. And now these induced permutations, these are the ones that define equivalence of those strings that encode my graph. Okay? And so that group I denote by Sn super 2. So what is Sn super 2? It is a permutation group of degree n choose 2. It permutes n choose 2 objects, but it is isomorphic to just Sn. It has n factorial elements, and it consists of the induced action of Sn on the n choose 2 pairs. Okay? So then two graphs are isomorphic if and only if the corresponding codes of lengths n choose 2 are G isomorphic under this particular group G. Okay? So you might ask, oh, okay, we can generalize this also to hypergraphs. So if you have a T-uniform hypergraph, then that can be encoded by strings of length n choose T. And then we get what I call a Johnson group, the induced action of the symmetric group of degree n on T tuples. These groups are going to play they play a central role in the analysis of a graph isomorphism problem. So for T-uniform hypergraphs, we have the same thing. Two hypergraphs are going to be isomorphic if and only if the corresponding strings of length n choose 2 are G isomorphic under this Johnson group action. Now, Johnson groups are intimately related to a particular class of graphs, and I should say that the terminology that I call these Johnson groups is not standard, but it is standard to call these graphs Johnson graphs, and so that's why I call the group also, corresponding group also Johnson group. So the Johnson graph has k choose t vertices, where k and t are two parameters, k is greater than twice the value of t. And naturally, if there are this many vertices, then those vertices are going to be labeled by t tuples of some, from some set of size k. So I take a set of k elements, and then all the t tuples of elements of that, so there are k choose t of them. These k choose t elements are going to be the vertices of my Johnson graph, and adjacency is defined by minimum distance. Okay, so if their difference is only one element, then I make them adjacent. So that's a graph, and the automorphism group of this graph is the Johnson group. Now, it is obvious that the Johnson group acts on this graph, so that the automorphism contains the Johnson group, but actually it is equal. The smallest non-trivial example of this is the complement of the Petersen graph. So the Petersen graph has five choose 2 vertices, and if you look at the complement, then you get exactly the Johnson graph J52. You can identify the vertices of this with pairs of points from a set of 5 elements, and you get the induced action of that group. That's again a beautiful little exercise for elementary connection between graphs and groups. Okay, now I'd like to talk a little about a classical heuristic that is basically the first thing that anybody would do when you want to discriminate between non-isomorphic graphs. Okay, so if we find irregularity in one of the two graphs that we are trying to compare, that helps. Okay, then I am looking for the same irregularity in the other. If I don't find it, then they are not isomorphic. I can refute isomorphism right away. If they are isomorphic, then I need to do some other tricks. So what happens if I don't find immediately any obvious irregularity, like in this case? Then what I can do is I simply create irregularity by assigning a special color to a vertex. I call this operation individualization. So now, however, this irregularity will propagate. So immediately the neighbors of this vertex are going to notice that they are neighbors of a start vertex. But for this particular graph, it stops there. Then, so now I managed to chop up my graph into 3 parts, but one of the parts is still bigger than half, so I didn't make sort of sufficient progress, and so I individualize another point. And once I did that, then irregularity propagates, and I end up with color classes of size at most 2, and then I say that, all right, I really chopped up this graph sufficiently well, and then I'll try to do something else. Now, individualization comes at a cost, okay? I did this chopping up at the cost of individualizing just 2 vertices, but what is the cost of that? Well, here is a notation. Iso xy is the set of all isomorphisms between the graphs x and y. And I write x sub little x for the version of the graph where I individualized the vertex x. Then in order to find all isomorphisms from x and y, I can individualize one vertex, and any one vertex of x. But then I have to compare it with individualizing all of the vertices of the other graph. Okay? So if I have an isomorphism between these two copies of the Petersen graph, then maybe it takes this start vertex to this start vertex. Or maybe it takes it here, or maybe here, or maybe here, or maybe here. Okay? So this incurs a multiplicative cost of a factor of n. If n is the number of vertices. I have to repeat, once I individualize the vertex, it blows up my cost. If there is a branching in the algorithm, depending on where that individualized vertex is going to go under isomorphisms. So I call this a multiplicative cost because what this means is that, okay, I reduced my problem to a more tractable problem, but not one instance of that problem, but a number of instances. So this is the branching factor in my algorithm. So if I individualize k points, then the multiplicative cost is becoming n to the k. And I must compensate that with significant progress. By significant progress, I mean that I reduce the problem size by a positive fraction. And my synonym for positive fraction is 10%, so I reduced it by 10%. I got a problem which is 90% as large as the original problem. Now let's see what kind of... Yes?
Reducing the size, you mean one color class will be of size 0.9?
I am speaking completely vaguely. Let's have some abstract notion of problem size. And then I have a multiplicative cost, and I am trying to just describe what a divide and conquer approach does to this. And then there will be concrete realization of how I achieve this kind of reduction. So right now I am just trying to set the goal. Okay? Basically, I am trying to explain what kind of things does one need to do in order to have a hope of having a quasi-polynomial bound. And so in order to have a quasi-polynomial bound, this is the basic inequality the basic recurrence that I'd like to have. I reduce the problem. So f of n is the cost of the of solving a problem of size n. Cost is best measured in this case in number of group operations. And that should be reduced to a number of instances of a problem of significantly smaller size, and Qn is this branching factor. Now, if this branching factor is Qn, and I am assuming it's f is a monotone function, then it is easy to see that the solution to this algorithm will be Qn to a constant times log n. Okay? I can only repeat this reduction log n times, and so I get a constant factor times log n in the exponent. So this is still quasi-polynomial as long as the branching factor was quasi-polynomial. Okay? So this is then the basic scheme that I am trying to employ. I am trying to reduce the problem size by a constant factor at the cost of, at a multiplicative cost that itself is still quasi-polynomial. That is going to be the goal, the basic outline. Okay. Now, I talked about refinement. Okay, so this is still classical heuristics. In fact, so classical that it came about before the definition of NP. So Weisfeier-Lehmann introduced a more sophisticated refinement method than the naive refinement that I was sort of describing, where vertices learn about colors of their neighbors. Weisfeier-Lehmann proposed to color not the vertices themselves, but the pairs of vertices, the ordered pairs of vertices. So that is basically coloring the complete directed graph. And there is a natural way of how you would refine such a coloring. So you do some appropriate counting so that a pair of vertices can definitely not be transformed into another pair of vertices if that kind of count is different. And then we generalize that to a k-dimensional version where the k-fold Cartesian power of the set of vertices is being refined. Again, there is a natural way of doing that. Immermann and Lander did it in the context of counting logic and got some very interesting results about this. So this is still a heuristic. And however, it is to be noted that k-dimensional Weisfeier-Lehmann supersedes any known combinatorial method, so purely combinatorial approach, combinatorial heuristic in trying to discriminate between non-isomorphic graphs. Now, it is obvious that k-dimensional wave-fair Lehmann refinement can be computed in n to the theta of k, so n to the constant times k steps, where n is the number of vertices. And the striking result of Zeifurer and Immermann from the late 1980s is that there exist pairs of non-isomorphic graphs that are indistinguishable by k-dimensional wave-fair Lehmann unless k is as large as constant times n. Now, if k is as large as constant times n, then n to the theta k is not even simply exponential, it is factorial magnitude, so that is completely then hopeless. So this eliminates the hopes of solving graph isomorphism just by pure combinatorial ideas. And so we need something else, and that something else, oh, I see, I should also mention recent follow-up on Zeifurer and Immermann. So graph isomorphism refutation by methods of group, various hierarchies of relaxation hierarchies in proof complexity also require omega n levels, which is the same thing as saying that they require essentially n to the n steps. This is true for the Sherali-Adams hierarchy, which is equivalent to Zeifurer-Immermann. And then there are stronger hierarchies, the sum of squares hierarchy, and even that requires omega n levels, even if we require the graph to be expanders. So it seems that there are now hardness results about graph isomorphism, that in certain models, graph isomorphism is provably hard. Now, group theory was introduced into the design of graph isomorphism algorithm in my paper from 1979. But in that paper, little more than the notion of cosets was used. So the notion of groups played a role. Cosets, you need to have groups for that. And Lagrange's theorem, and really essentially nothing else. But the theorem that followed from that was that if we have a vertex-colored graph, where every vertex color has bounded multiplicity, so there are only a bounded number of red vertices and bounded number of green vertices, etc. Now, coloring means that colors are preserved by isomorphism by definition, so colors cannot be switched. Okay? So that kind of isomorphism problem that still allows exponentially many bijections. However, it can be solved in polynomial time. But the funny twist is that the Zeifurer-Immermann graphs can be actually viewed as colored graphs with color class size 4. So even the most naive application of group theory already beats these examples that are intractable for any purely combinatorial approach. Okay, I should qualify my result a little bit. It was not deterministic, it was Las Vegas. Anybody knows what's a Las Vegas algorithm? Show of hands. Not many hands. Okay. Anybody knows where that term was introduced? In this paper. Okay. That was my first appearance at a Fox or Stock conference. It was in Puerto Rico. So anyway, this algorithm was then subsequently, very soon, de-randomized by Fürst-Hoptroff-Laft, and subsequently 20 years earlier by Sims, who did algorithms in computational group theory that actually did work even on the computers of the time. That's quite something. And then it was all clarified by Don Knuth. So anyway, the real power of group theory came with a subsequent paper by Jean Lux. And this is the single most important paper you would ever read on graph isomorphism. Okay? So this paper introduced group theoretic divide and conquer methods that allowed the application of group theory in depth. The title of the paper is Isomorphism Graphs of Bound Valence Can Be Tested in Polynomial Time, and that's the result that we don't use, okay? What we do use is Lux's method, Lux's framework. That's wired into the genes of the current algorithm. So if you want to understand how this algorithm works, the first thing to do is read Lux's paper, okay? I mean, in my paper, I try to explain it, but really, read the master. So the method the method of choice really is a combination of group theory and combinatorics. So we don't throw out those methods. The individualization refinement is a central part of this algorithm, but it is combined with group theory, and then it becomes a very powerful tool. Actually, this kind of combination was already foreshadowed also in my 1979 paper, where I proved that graph isomorphism for bounded valence is exponential in square root of n. All right, now this was essentially ridiculed a year later by Jean-Lux's algorithm that the same problem can be solved in polynomial time. However, the idea that we have to combine these two types of methods, that survived and had applications back then and later and more recently in these papers. I should mention that in 1982, we proved the result with Cameron and Palfy in group theory. That's a pure group theoretic result that was highly pertinent due to kind of application of group theory that Jean-Lux needed. And so this was basically somehow a determination of the ultimate limits of the power of Jean-Lux's method. And no new group theory has been added since 1982. I mean, a lot of people use group theory and Lux's method for various cases of the graph isomorphism problem, but no actual new group theory has been added. Now, so there is something new now, and that is what I already stated, the unaffected stabilizer theorem. That's the chief new divide and conquer tool. And then there is a group theoretic algorithm, which I call the local certificates algorithm. And these two constitute the heart of the entire paper. Further ingredients are, okay, so we construct what I call local certificates. These local certificates then have to be aggregated to fullness or non-fullness certificates. I'll explain what that means. And then there are combinatorial partitioning algorithms that come in two steps. One I call design lemma, the other I call split and Johnson lemma. But I should emphasize that the heart of even though these are technical and constitute maybe half of the paper, the heart is the group theory. That's the thing that happened on the 14th of December, and until then I was completely in the dark, and after that everything was clear. So, I hope that you are going to poke into the details everywhere, but I can tell you, if you find a mistake here or here, then I am going to just hang myself, because then everything is gone. On the other hand, if you find a mistake here or here, then I will just say, okay, give me a day or give me 5 minutes. I have a bag of tricks, and these things I am not concerned about you know, all the details of that. So, okay, so first a 2-minute overview of permutation groups. So a permutation group is a subgroup of the symmetric group. If I write the less than or equal sign, that means subgroup in this context. And omega is the domain on which it acts, and it will invariably have n elements. Two of these symmetric groups are two of the subgroups of the symmetric group are much larger than anything else. The symmetric group itself and the alternating group, which is the group of even permutations. These two I call giants to avoid always having to say either the symmetric or the alternating group. So it's the giants. So the giants on a particular set are not smaller alternating groups or so. These are the symmetric or alternating group on the entire set. A subset is, I say that it is G invariant if every element of the group G transforms that subset into itself. An orbit of a permutation group is a minimal G invariant subset, so two elements are in the same orbit if one can be transferred into the other under the group action. So the orbit of an element is simply the set of all images of that element under the group action. A group is called transitive if there is just one orbit, okay? So every pair of elements is equivalent under the group action. And once again, the stabilizer of an element is just all the elements of the permutation group that fix that element. And an easy counting fact, a little homework if you haven't seen it before, that the index of the stabilizer is equal to the length of the orbit. The length of the orbit is the size of the orbit, so how many elements it has. Now, suppose that we have a transitive group, then there is further structure that we want to look into. A block of imprimitivity is a block of a G invariant partition. So now I'm talking not about G invariant subsets, which have to be preserved, but G invariant partitions where the partition is preserved, the blocks themselves not. The blocks can be permuted. A primitive group is a group that has no non-trivial invariant partition. And if I look at the G action on the blocks of a minimal invariant partition, meaning the blocks are maximal, then that's a primitive group. Now here is an example. If you look at the group of symmetries of the hexagon, then this is an imprimitive group because for instance, here are the two blue blocks. Some of you will recognize this. And so that's a system of imprimitivity. These blocks can be permuted but cannot be distorted. And there is another one, another partition into 3 blocks, and that's also an invariant partition. These blocks can be permuted among each other but cannot be distorted. So for instance, a blue one can never be transformed into a red one. Okay? On the other hand, if I look at the group of symmetries of the pentagon, then of the regular geometric pentagon, then that's a primitive group for the simple reason that it has a prime number of points, so I cannot divide it into blocks because the blocks would have to have equal size. But this is, of course, no indication that primitive groups would necessarily have prime degree. Most important for our purposes is that the Johnson groups are primitive groups. Okay, so the Johnson groups have act on n choose t points, and they are primitive. Okay. So let me get back again to the string isomorphism problem. Our goal will be not just to solve the decision problem, whether or not 2 strings are G isomorphic, but to find all G isomorphisms. So the set of G isomorphisms is just the set of all those sigma that transform X into Y. The G automorphism group is just the group of isomorphisms of G with itself. And, it is an obvious fact that if there is a G isomorphism, so if X and Y are G isomorphic, then the set of all G isomorphisms is a coset of the automorphism group. Okay, so to get any G isomorphism, I can apply an automorphism, an arbitrary automorphism to X, and then follow it by one particular isomorphism. Okay, so now one piece of significance of this is that then for the set of G isomorphisms, we also have a concise representation. Namely, we give generators of the automorphism group and specify just one isomorphism. Okay? All right. You might ask, okay, we only need to solve this problem for a very special Johnson group. Why do we have to look at all groups G? The reason we do this is because we are going to do recursion on the group. So the group gives us a huge degree of new freedom where we can modify our input and reduce things. So by definition, the group of G automorphisms of X is a subgroup of G. Okay? That's by definition because we are only considering elements of G as G automorphisms. But when we have a trivial inequality, we may be interested in the case of equality. So what happens if the group of G automorphisms of X is all of G? First of all, I'd like to mention that this condition is easy to verify. How do I verify? How do I decide whether or not this is true? Yeah, I just checked the generators. Okay, if every generator of G is an automorphism of X, then this equality holds. But now my next question is, if the answer is yes, that this is true, then we have a very easy, then we smile. Then we have a very easy way of deciding whether or not 2 strings are G isomorphic. A vagueness test. I'd like to see a very simple statement on this other side, a very simple statement. So if the automorphism group of the G automorphism group of X is all of G, then X is G isomorphic to Y if and only if David shut down or shut up. Somebody else. If and only if they are equal. Okay? Because what does it mean they are G isomorphic? That X can be transformed by an element of G into Y. But if the G automorphism group of X is all of G, then X is transformed into X only. So they are isomorphic if and only if they are equal. Okay, so that's fine. Then we are happy. So basically, that will be always our running hypothesis that we keep trying to refute. Okay, if this is equal, then we are fine. And otherwise, we are trying to refute it. But of course, we can refute it because we can decide whether or not it is true. But we want to constructively refute it. It's not enough to say no. I want to something positive. I want to have a witness. I want to have something that demonstrates that they are. So one such thing could be a smaller subgroup. So that's a goal. Okay? If if the G automorphism group of G is not all of G, then it is a smaller subgroup, and of course I can't immediately find that smaller subgroup, but maybe I can find an intermediate subgroup. I want to encase the automorphism group into a smaller group. It is into a proper subgroup of the current G. So that will be the kind of reduction step that we are looking for. And then I should mention, if I can do this in a sufficiently constructive manner, then I can actually perform an alignment step. I change my other input in such a way that change is explicit and easy, and it turns my input into something that is G isomorphic to it, but it reduces the question of all G isomorphism between X and this new input to H isomorphism problem of these two. And let me really, for this, let me give you a picture. So, for instance, if I have two graphs and they have colored vertices, and imagine they have the same set of vertices, I'm just drawing two copies, okay? So this has the same set of vertices, and one of them has red vertices, and the other also has red vertices, and then it has some blue vertices, and this also has some blue vertices, and then it has some green vertices, and this has also some green vertices. This white is called green, okay? All right, then what I can do is, first of all, I compare. Do they have the same number of red vertices? If I don't, then I immediately refute isomorphism. But if they have the same number of red vertices, then my alignment step will be that I simply apply a permutation to the set of vertices so that the red vertices match the red vertices here and the blue vertices match the blue vertices here. So now, for both graphs, I'm going to have the same coloring of the vertex sets, and so the isomorphisms will no longer be just any subgroup of the symmetric group here. It will be subgroups of the product of the symmetric groups of the color classes. So I encased my set of automorphisms, and in fact even the isomorphisms I encased into this smaller subgroup, and that's the kind of thing that is being stated here, but this is a more general principle. Okay? So this strategy allows recursion on the group G, okay? Now, what we need actually is not G isomorphism where G is a group, but we need isomorphism within a coset, which is defined in exactly the same way. So suppose we have a coset of a subgroup of the symmetric group, then I may be looking at all isomorphisms that belong to that coset, okay? So the definition is identical. I mean, I could have this definition for any subset of the symmetric group, but we are only using it for cosets. But using it for cosets and not just for groups is important. However, the next thing I want to say is that it is not more general than looking at just groups. So it is straightforward to reduce the isomorphism problem within a coset of G to the isomorphism problem within G. Okay? I just have to apply the inverse of this permutation to the second, and then in the end multiply by pi. Okay? So this is more general, but it is not. Okay, but here is a place where it will be clear why this is advantageous to look at it as from cosets. One of the major reduction steps that Jean Lux used back 35 years ago was this. Okay? Suppose we have a subgroup of G. Then G isomorphism reduces to a number of instances of H isomorphism, the number of instances being the index of this subgroup. And this is based on this straightforward identity. Well, we know that G is the union of the cosets H pi. Okay, R is just the set of representatives of that coset. But if G is a union of this H pi, then the set of G isomorphisms is a union of the H pi isomorphisms of these strings. Okay? So, so this way, what we got is, we got it reduced G isomorphism to isomorphism with respect to cosets of H, but in fact what that means is that it is reduced to isomorphism with respect to H. Okay? All right. Now, another important thing that Jean Lux observed, although this has its predecessor, a precursor already in my paper, is looking at windows. Okay, so I don't look at the entire input at once. I take a G invariant subset, and I only consider the input within that window. So imagine the input is everywhere, but I only see that part. And that part is that I am trying to observe. So the set of G isomorphisms with respect to that window is the set of those elements of G that preserve the restriction of the string to that window. Okay? And they do anything elsewhere. They act on the entire original domain, but I don't care what they do there. Okay? And so this is a very powerful, this gives a very powerful recurrence, namely if omega is partitioned into G invariant subsets, then we can simply process this window by window. So first I align the inputs on the first window, then within the sub-coset that I got, align it in the second window, and etc., etc. If at any point I get empty set, then I'm done. If it's not, then I get a sub-coset, and that is going to be. Now let's see what kind of recurrence do we get here. Well, this is an extremely efficient recurrence. It is linear except for the overhead. If there is some substantial overhead, then it will be essentially equal to the overhead. So that is the cost of this reduction. So this is, if the sizes of those windows are substantially smaller than the original, then this is an extremely efficient recurrence. So now this will occur and will be used in combination with the descent. Descent is costly. If I descend, then the cost is the index of the subgroup to which I descend. However, if the subgroup to which I descend actually has orbits that are small, then I can recover my cost, and that is the basic idea. Okay? One fact to remember is most often this is going to be used in the following context. The group G is transitive, and we have a normal subgroup. Now, if I have a normal subgroup of a transitive group, then the orbits of that normal subgroup equipartition my domain. They divide it into equal size subsets. So the orbits of a normal subgroup of a transitive group are of equal size. So the only thing I have to ensure is that the normal subgroup itself is not transitive. Of course, it could be that the normal subgroup is transitive, but if it is intransitive, then I made significant progress. Then the orbits are at most half the size. And so in that case, I get a substantial reduction. Okay, I call this previous rule, this is the chain rule, okay, this orbit by orbit processing. And then if I have a descent to such a normal subgroup and then apply the chain rule, then this is going to be an efficient recurrence, okay? Assuming, of course, that the index is small, and now I have to quantify what I mean by small and what I mean by efficient. Well, for this paper, by small, I mean quasi-polynomial, so I have to descend to a normal subgroup that has quasi-polynomial index, and efficient means that the recurrence then becomes quasi-polynomial. So now, okay, so the algorithm starts by using Lax's algorithm. Lax's algorithm is a divide and conquer algorithm. If there are orbits, we process them by orbit. Then we look at just one orbit. If there are domains of imprimitivity, then we try to descend to that normal subgroup. So the question then is, what is the action on that normal subgroup? And if that is large, then we have a problem. Okay? And the fact is that this situation can be characterized using a result of Peter Cameron from 1981. So Cameron determined all primitive groups of order greater than n to the log n, essentially, and all of them are essential. They are essentially, this is not entirely correct, but essentially Johnson groups, and so they are isomorphic to alternating groups or symmetric groups. Okay, so Johnson group, I extend the definition that it is not necessarily the induced symmetric group, but can be the induced alternating group. These two cases just come hand in hand. And so what we find is that if Lax's algorithm bogs down at a certain point where it would be too expensive to do the descent combined with the chain rule, then we magically have some other domain on which the group acts as a giant. And the size of that domain, this M, goes in the exponent of the running time of Lax's algorithm. So we are fine as long as that other domain has size, polylogarithmically bounded size, but we have a problem when it is greater than that. In fact, we are going to draw the line at just constant times log n. And yes?
What used to be T, the Johnson
I'm now, so the Johnson group is out now. M is the size of this new domain that just arises magically from the study of the structure of the groups where Lax's algorithm bogs down. Okay? So once again, if I have a permutation group where Lax's algorithm does not work efficiently, then that means, and in fact it will be efficiently constructed, and we shall efficiently construct an action of that group on some other domain. And that action is a giant action, so it is either alternating or the symmetric group on, on that other domain. So that domain gamma, I'm going to call that, so here is a picture, okay? So omega is the set of positions where my input string resides, okay? And what we find is, we ignore the string for now and we only focus on the group G, and this group G has an epimorphism onto a giant on some other gamma. I call that the ideal domain. And actually, all the action is going to occur in the ideal domain. So, okay. So this is the barrier situation. Barrier situation is when the group has an epimorphism on a giant on some non-negligible sized set gamma. And then our goal will be the following. So I look at this homomorphism that maps G. But what I am interested in is not what is the image of G. I already know what is the image of G. I am interested in what is the image of the G automorphism group. And of course, that I don't know. But I want to either confirm that the image is the full giant. So this is an analogous situation like the trivial situation that I began with. I will indicate why we are happy if the answer is yes. I will indicate why we can test this and why we are happy if the answer is yes. But if the answer is no, then I want to break the symmetry gamma. Okay, so then I know that the image is not actually all of the symmetric or alternating group on gamma, and I want to break this symmetry. Okay, and I will define what I mean by breaking this symmetry. Okay, so the first thing is we have this homomorphism, and then let's look at the kernel of that homomorphism. Okay, so that's a normal subgroup, and it is a fact. I will indicate why it is true that this group is intransitive. And also we know that its orbits equipartition G, so going down to this kernel is major progress. If we can do that in a way that's less expensive than a naive application of Lax's descent. So, okay, so the next thing that we have to study is, okay, we have this symmetric group action on the ideal domain. Let me pick a permutation of that, and let me try to lift it. Well, I can definitely lift it to an element of G, but can I lift it to an element that is an automorphism of my string? That will be a crucial question, and the answer to this is that this is a k-isomorphism problem. So for any particular permutation of the ideal domain, I will be able to determine its lifting to automorphisms of the string by efficient Lax recursion, because it brings my group down to the kernel of this giant homomorphism. Okay? So, okay, so once again, the goal is either to confirm that the automorphism group already maps to this giant, and this is a testable condition then. This is a testable condition because it is true if and only if every 3 cycle acting on that ideal domain actually lifts to an automorphism, and that lifting is decidable. I can decide it by looking at all 3 cycles and lifting all of them. If all of them lift, then that means that the entire alternating group lifts to automorphisms. And of course, I only need a connected set of 3 cycles, so much fewer trials are enough for this. So if the answer is yes, then actually the set of all G isomorphisms of X and Y have been found using a small number of instances of K isomorphisms. So that's a very efficient recurrence using Lax's technique. So now, okay, I am making a little jump here The other extreme is if none of the 3 cycles lived, and the intermediate cases are of no concern. Basically, if I have the intermediate cases, I will have some chopping up. The goal is to chop up the domain gamma. The intermediate cases allow me to chop them up. And so essentially only the other extreme will be of concern when no 3 cycle lives. And then, of course, the first goal goes away. And the only thing that remains is I want to break symmetry, the symmetry of gamma under this assumption. Okay? All right. So now I'm going to describe ways of what I mean by what kind of output is going to break that symmetry. If I have a canonical coloring, meaning a coloring of gamma that is preserved under G isomorphisms, okay? So imagine I have 2 inputs, x and y. I am explaining canonicity, okay? I have 2 inputs, x and y, but I have the same group G. I have the same homomorphism. I have the same ideal domain gamma. And now I am coloring gamma. Every isomorphism of x and y, of my original strings, by way of my homomorphism, induces a map between the 2 copies of gamma. If that preserves, I say that this is a canonical coloring. So a canonical coloring is basically a procedure that assigns this, and I apply that not only to the input string x, but also to the input string y, and then I have then it means something what happens if I apply an isomorphism between x and y. Okay, so all right, so this is this is what it means for a coloring to be canonical, but the same definition, yes. Well, I'm just defining what it means for a coloring to be canonical, and one of the goals is, I mean, if I can compute a coloring which is a good coloring, I will define that, then canonical, it has to always be canonical. So I'm trying to compute canonical objects, but right now I'm just trying to define what it means that they are canonical, okay? So a canonical partition will be an important thing. Okay, meaning is again the same. I partition gamma for x, I partition gamma for y, and then every isomorphism of x to y induces a mapping that maps one of the partitions to the other partition. Okay, and actually I can do this with any object. So I can put a graph on the set gamma, and that's canonical if that graph, if the isomorphism of the original strings induces an isomorphism of those graphs. Okay. So that's one word that defines what it means to be canonical. Now, okay, so how can I break symmetry? So first of all, one good way would be find a good canonical coloring, which means that every color class is at most a 0.9 fraction of gamma. Okay, that will be a good outcome. Another possibility is find a canonical coloring where, okay, there is a dominant color class, the color class is greater than 90%, but that color class is equipartitioned non-trivially, okay? So that's again, that again will be a happy outcome. In that case, the problem size is going to be reduced to the number of blocks. So, okay, I have to refine, previously I said something, how do we get this quasi-polynomial complexity, and I have to refine it because we are actually going to work in 2 parameters, n and m. N is the size of the original input, and m is the size of this ideal domain. And all we know about the size of this ideal domain, m, is that it is less than or equal to n. It can be as large as n. And so the previous fn, which is the number of steps, is going to be gnn. But then, the progress that we are making is going to be not by reducing n, as Lux would require, but we are reducing m. So we are reducing the size of the ideal domain, and so this will be then the basic recurrence that we are reducing the size of m without reducing n at a multiplicative cost. Okay? And now, when the size of m goes down below some threshold, a cutoff point, say polylog, at that point we just individualize every point of the ideal domain, and then that causes the original domain, the real world domain, to also split sufficiently. Okay? So when we reach that point, then we get down to having significantly reduced the original domain size. So if you combine these 2 recurrences, then what you see is a log squared added to the exponent, because we reduce the ideal domain in log n rounds before we achieve one step of reduction of the original domain, and then everything starts over. Okay? So altogether, this is log squared iteration, so we get log squared. But what this says is that if our branching factor is quasi-polynomial, then even this is still quasi-polynomial. Okay. So the goal is to break symmetry. And the way we would want to break symmetry is really to construct some intermediate subgroup, some subgroup that already includes the automorphism group, and we cannot do that directly. But at least first, we should have some explicit evidence of this reduction. So for instance, if we find a canonically embedded non-trivial regular graph on 90%, at least 90% of the vertices, that's a good indication of reduction, and that's going to be our intermediate goal. So before trying to actually explicitly reduce the group, we want to find an invariant structure. There was no invariant structure to begin with. On the ideal domain, we had the action of the entire symmetric group. So if instead I can point out that here is this regular graph, for instance, which is canonically embedded there, then that means that I already implicitly significantly reduced the group gamma. Okay? I reduced it to the automorphism of this. It's easy to show that this means actually an exponential reduction in the order of the group acting on this gamma. Now the question is then, once we have this graph, then we try to use this graph to find what? A canonical coloring or a canonical partition. Okay? Just using this graph. So I forget the original inputs, I just have this graph and I try to reduce this. I can do individualization and refinement, whatever I want, and I try to get a reduction. So question is, can we find a canonical and good coloring or equipartition at a modest multiplicative cost starting from a regular, non-trivial regular graph? And the answer is no. The Johnson graphs are tremendously resilient. They are resilient to good coloring or partition. So recall the Johnson graph. The vertices of the Johnson graph are the t tuples of a set of elements, and two of them are adjacent if the corresponding t tuples, their labels, differ minimally. And one can show that the multiplicative cost of a good coloring or a partition is exponential in k over t. Now, t can be as small as 2. So that's a very important case, in fact. In fact, in that case, we have k being essentially square root of the original set of vertices, and this is the square root that prevented progress for 30-some years. So, so k can be a constant, and so this is going to be an exponential in that k, but k could be square root of the original number of vertices, so the multiplicative cost could be exponential in square root, so we make no progress whatsoever. What happens, and this is easy to see, that if we begin individualizing a small number of vertices of the Johnson graph, then that individualization, that irregularity propagates to some parts of the Johnson graph, and still a huge Johnson subgraph remains, completely intact. So Johnson graphs are just a huge headache in this study. But then, Johnson graphs are the only obstacles to efficient partitioning. So here is the formal result. If we have a non-trivial regular graph, then at quasi-polynomial multiplicative cost, we can either find a good coloring, or we can find a canonical equipartition of a large color class, or we can find a canonically embedded Johnson graph on a large part of the graph, or a large part of the set. So this is one of the two main combinatorial partitioning results. Okay, so either we can split our graph, or we find a Johnson. Now, I already indicated why it is good if we can split the graph. But why is it good if we find a Johnson? Well, let's see. If we find a Johnson graph, then the Johnson graph is defined on some smaller number, at most square root-ish number of points. And the automorphism group of that Johnson graph is just the symmetric group on that number of points. So all of a sudden, the value of m is the size of the ideal domain to which we have a giant homomorphism. But now we have a giant homomorphism into the automorphism group of that invariant, of that canonically embedded Johnson graph. So that's a much smaller value. So if we could continue doing this, we would be done not in a logarithmic number of rounds, we would be done in log-log rounds. I mean, of course, we cannot do this. This is not going to continue. But all of a sudden, okay, what? Okay, so what I want to say is here is that it turns out that Johnson graphs, once we discovered them, are tremendously helpful. They give us a recurrence that is much more efficient even than good partitioning. Okay, so actually, we are not going to immediately find a canonical regular graph. A regular graph is a binary relation. Instead, we are going to have a canonical k-ary relation for some logarithmic value of k. That's also an indication of much reduced symmetry. But of course, not any k-ary relation will work because if I have a k-ary relation that has the symmetric group for its automorphism group, so it's essentially a trivial relation, then of course I didn't get anywhere. So I have to somehow restrict my type of k-ary relations that I'm looking for. And so here is the next central definition, which is again a very simple thing, but it is the key thing for the recurrence. So if I have a structure x, this script x, so I have a structure. This could be a relational structure. So I have just a list of k-ary relations.
It's basically a hypergraph instead of a graph.
Well, it's not, because it's rather a directed hypergraph. Okay, so the k-tuples are ordered. So this is sets of ordered k-tuples are colored. So, so there is a red set of k-tuples, a blue set of k-tuples, etc., and colors are preserved by definition by isomorphisms. Okay, and now let's look at a subset of the set of vertices. Suppose that the symmetric group acting on that subset is inside the automorphism group. So what I have here is that I can permute arbitrarily that set delta while I fix every other point. If these are automorphisms of my structure, then I say that this is a symmetric set for that structure. And then the symmetry defect of X is how large the complement can get. Okay, so that's the smallest, how small the complement can get. So the symmetry defect is going to be the size of the smallest subset of my domain such that the complement can be arbitrarily permuted. So that's what I call the symmetry defect. So here is an example. Suppose that my structure is divided into two parts and there is no structure within those parts, so the automorphism group is simply just the product of the symmetric groups on those two parts. In that case, the defect is going to be just the minimum of these two. Okay? So if I fix every point in delta 1, then I have exactly the symmetric group of delta 2 acting here. Okay? All right, so this is the notion of the symmetry defect, and then the point of our recurrence will be that we start off with something with a non-negligible symmetry defect, and throughout the recurrence, this is going to be the condition that we are trying to preserve. Okay? And so here is the lemma that reduces the k-ary relations to binary. Assuming that we have a k-ary relation with non-negligible symmetry defect, say 10%, which means that no symmetric group greater than 90% can act on it, then at a multiplicative cost of number of points raised to the power essentially k, where k is the arity of my relations, either I can find a good coloring or a canonical equipartition of a large color class or a canonically embedded non-trivial regular graph on a large fraction. So this basically brings me down to that situation that I described before. And then once I am down there, then I can use split or Johnson, and that brings me down to the three possibilities: good coloring, good partition, or Johnson. Okay, now I'd like to, again, just review the unaffected stabilizers lemma. So remember that if I have a giant homomorphism, then an element of the domain is, I say that it is affected if the stabilizer of it is not mapped on a giant inside the domain gamma. Okay, and then the unaffected. So I'm varying it a little bit. Previously, I only stated it for the alternating group. This is not a significant difference. This is just the same thing, but it is more convenient to use it this way. That instead of requiring an epimorphism onto the alternating group, I require an epimorphism on a giant, whichever giant. The giant can always mean one of the two. They don't have to be in the same context. Even the two giants don't have to be the same. And so that's what is happening here. Okay, and so then what this lemma said was that if m is greater than essentially log of n, so if the size of the ideal domain is at least logarithmic in the size of the original, in the number of positions on which my strings are defined, then if I look at all the unaffected points, then their pointwise stabilizer still maps onto a giant on the ideal domain. Okay, that's the unaffected stabilizer's lemma, and I already had this sequence of drawings, but just to recap, that's what happens. Now, this lemma has this corollary, and I also mentioned this. Now, this is there's a companion result to this lemma, which I call the affected orbit lemma. So already I have to explain the name. I defined what it means for a point to be affected or not affected, but this is something that is an invariant of the orbit. If two points are in the same orbit and one of them is affected, then the other is also affected because the stabilizers are conjugate subgroups. Okay? So here there is no magic number here if the domain size is at least 5, so I'm just ensuring that my giants are not solvable. Then the kernel of this giant homomorphism is not transitive on delta. Now you remember the significance of this. If I have a normal subgroup of small index which is not transitive, then I can efficiently Lux reduce my problem if I can get down to that kernel. Okay? So in fact, what this is easy to prove. This is a triviality, that each k orbit has lengths, its original length divided by the the size of the ideal domain. Okay? Okay, so now I have to get to the local certificates thing. Basically, I am not able to directly treat the entire ideal domain. I am going to pick a small subset of that, which I call the test set. If it is the case that somehow a large group acts on the ideal domain, then of course a large group is going to act on the, I mean a symmetric group or what, and a giant acts on the domain, then of course giant is going to act on the test set. But now I am going to show first of all that I can decide whether or not actually a giant acts on the test set. So let's look at a subset of the ideal domain of size t, where t is just the rounded up value of this logarithmic quantity so that I can apply the unaffected stabilizer's lemma. Okay, so these are logarithmic size subsets of my ideal domain, and remember that the ideal domain can be as large as n, or in critical cases it's square root of n, but it can be also as small as some constant times log n. And now let's look at the setwise stabilizer of this t. So this is setwise stabilizer. So for pointwise stabilizers, I use parentheses, and for setwise stabilizer, I don't use parentheses in the subscript. So we look at the setwise stabilizer of t in G. G is a group that was defined as acting on omega, but there is this homomorphism by which it also acts on gamma. So I can pick an object in gamma, and I can look at that subgroup of G that stabilizes that object. Okay? And then what I do is, okay, so this subgroup, the stabilizer of my test set, that maps into the symmetric group. Of course, it fixes that subset, and then I can restrict it to that subset. So the combination of these two homomorphisms I denote by psi sub t. So psi sub t is a homomorphism of the stabilizer of my test set in the group G to the symmetric group acting on the test set. So here is a picture. And I am, okay, I am going to, oops, yeah, just illustrate it. Okay, so here is my omega, and you can see that there is this input string but we are not considering the input string right now, but that's the domain on which the input string is defined. And we select a test set which is a small subset of my gamma. Okay? And then here is the restriction of my homomorphism to just from here to here. Okay? So now let me define what the categorization of the test sets. So there will be two kinds of test sets, full and not full. The definition is this: a test set is full if the automorphism group of the string already maps onto the giant on this test set. Okay? So it either does or it doesn't, and this is the question we want to decide. It is full if it does. So once again, if I look at just the group G sub T, that maps onto a giant, in fact onto the symmetry group on T. But the automorphism group is smaller, and I don't know what the automorphism group is. But my question will be whether or not that unknown automorphism group still maps onto a giant. I call it full if it does, not full otherwise, and it may come as a little bit of a surprise that we can decide this with efficient Lux reduction. Okay? But I want to not only decide this, I also want to get meaningful certificates of each outcome. So I have to define what I mean by a fullness certificate, and I have to define what I mean by a non-fullness certificate. The fullness certificate is easy to understand. Fullness certificate is simply a subgroup of the automorphism group of X, subgroup that fixes the set T setwise, such that that subgroup already maps onto a giant on T. If I can produce such a subgroup of the automorphism group, then obviously the entire automorphism group also maps onto such a giant. So I call this K of T a global object because it consists of automorphisms of my entire input string. Okay? So this is also an easily verifiable object. If I produce that subgroup, you can verify whether or not it does consist of automorphisms of the string, and also whether or not it maps onto this giant. Now the non-fullness certificate, this is going to be a local object. This is going to be simply a subgroup of the symmetry group acting on the test set. So this is a tiny thing. What kind of subsuit? It's going to be a subgroup which is not a giant, but it encases the image of my automorphism group. So somehow it should come with a guarantee that if I map my automorphism group to the test set, then everything there is going to be contained inside this smaller subgroup. Okay? Now, if I give you this certificate, you have to take my word for it that it works. So in the course of the analysis of the algorithm, we are going to prove that the certificates that are produced are actually, they satisfy this. Basically, what is going to happen is that these subgroups are going to be images, not of the full automorphism group, but the automorphism group of a string on a window, and on a canonically selected window. And so that's a bigger group than the automorphism group, because we are only worrying about the subset of the input, and that already maps onto this. So that will be verifiable by recurrence. Okay, so this is the theorem that we can decide by efficient Lux recurrence whether or not T is full, and find these types of certificates for each outcome. Okay, all right. So okay, so what's a window? Window is just a subset of this domain on which my string is defined, and the partial string corresponding to a window is that I make the input, that part of the input, visible. Okay, so x to the w denotes the restriction of the input string x to this window w, and then I am going to use this notation, AGW. What is this? This is the set of those G automorphisms of x which respect this restriction to the window. So I don't know what happens with the rest of the input, but this part of the input is respected. And of course, there is an analogous definition for isomorphisms. Okay? And now I give you the central algorithm of the entire process. This is the core, this is the key, everything depends on this. This is September 14, the previous year. Okay? So this is the procedure. So there will be a current window, which I will refer to, for some reasons to be clear in a minute, I refer to it as a beard that keeps growing. This window will keep growing, but I can't really visualize a window that's growing. I can visualize a beard that is growing. And and initially, it will be the empty set. So it starts off being the empty set. I start with an empty window. And what I am going to do is, I will always look at the automorphism group of the partial string that I can see through this window. Okay? So here is the procedure. So we initialize the window to the empty set. So the corresponding automorphism group is simply just this group, the original group fixed stabilizing this test set that we are currently considering. Now there will be a condition under which so this is a while loop. We keep updating the window. How do we update this window? The window will be, we take the previous window and add all the points that are affected by the current automorphism group. So we have a current window. That current window, if we are lucky, then it has an automorphism group that still maps as a giant to T. Then affected points make sense. And then I add these affected points to the window. Now, I should remark that I need not say that I add any points. I just look at the affected points by this subgroup, because the group keeps going down. As I keep increasing my window, I consider a bigger and bigger portion of my input, and therefore the group becomes smaller and smaller. But a smaller group affects more points. That's, again, an obvious statement. The group is smaller, then the stabilizer is smaller. The stabilizer has a better chance of not mapping onto the giant. Okay? So that means that this beard keeps growing. And now here is the illustration. Okay? So this was a little too dense, but the illustration will maybe clear. So we start from the points that are affected by just the original group G, the ambient group G, restricted to fixing T. Okay? So this group has a giant homomorphism onto T, and then there is a set of points that is affected by that. Actually, we have a theorem that says that at least one point is affected. So this is a non-empty set to start with. And so our initial window was the empty set, and this is going to be the window after the first round. Okay? And then we all of a sudden see the input through this window. And we reduce our automorphism group so that it will now consider the letters of the alphabet that are in this window. And then we repeat. We get now a smaller group. This smaller group affects more points. The beard is growing. We are going to see what's the input in it, and we repeat. Okay? And then at some point, this procedure is going to end. Okay? So, the question is, how does the while loop end? I didn't write out the while condition, but now let's decide what is the condition. Well, there can be two reasons for the loop to end. One is that our automorphism group that kept shrinking became so small that it no longer maps to a giant. That's one possibility, then we end. The other possibility is that somehow the beard stops growing. The group is still mapping onto a giant, but no new points are affected. Okay? So the group shrank. Nothing is to tell us that if the group shrinks, then the number of points affected grows. It is just not going to be smaller. And so these are the two cases in which we stop the while loop. We exit the while loop, and now my question to the audience is, which of these two cases corresponds to fullness and non-fullness? So in one of these two cases, the automorphism group will map onto a giant on the test set, and in the other case, it will definitely not. And the question is, which case is which? And I would prefer if you raise your hand when you know the answer so that others can maybe think a little. Yes? No, you didn't? No, sorry. Anybody? I lost the entire audience. Yeah. Yes? The first is non-full, yes. Yes, it should be clear that in the first case it's non-full, because we have a partial string, And its automorphism group already does not map on a giant. So necessarily the full automorphism group doesn't map onto a giant. So this case corresponds to non-fullness. And we have to show that when the beard, if we stop because the beard stopped growing, that means that the group was still mapping onto the entire thing, but that's only an automorphism group of a partial string, so we don't quite know. But if I am right that this other case corresponds to the other case there, then that's what it should be, but I haven't proved that. Okay, so so the first case obviously leads to a non-fullness certificate, namely the image of this group that we had, but the second case is not clear at all. Okay, so in any case, so this is case A. Case A, the non-fullness certificate is simply the image of the current automorphism group. For B, we need a subgroup of the automorphism group of the string that maps onto a giant. Okay, now, this group that is an automorphism group of a partial string does map onto the giant in this case, but it only respects the part of the input that's in the window. So how do we create now a group that actually respects the entire input and still maps onto the entire giant? Anybody have a guess?
You can continue on the rest.
I can continue on what?
Continue on the remaining part of the input.
So the remaining part of the input is unaffected points, and I don't know what I could continue because I was always adding affected points, and now I got stuck. No, the beard is not growing. Well, I look at the pointwise stabilizer of that current automorphism group, the pointwise stabilizer of the unaffected points, which is the entire complement of my current window. The complement of the current window consists of unaffected points. That's why we stopped. And I take the pointwise stabilizer of that. Okay, I have to verify that this group now does two things. One of the things is it maps to a giant. Now, why does it do that? Oh, that was the unaffected stabilizer theorem. And the other thing, what is the other thing I need to verify about it? You see, this group here consists of partial automorphisms. It's only automorphisms of the string in that window. How did I all of a sudden get full automorphisms? Well, let's look at this. So the question is, why did I get global automorphisms after doing this pointwise stabilization? Okay, so I look at my group, and obviously it is going to respect the strings that are inside the window because it was a subgroup of a group that already respected that. So there is no problem with that part. But okay, here is this letter B. Why is this B respected by my new group? Okay, so respected means that this B is taken to a B by any element of the group that I have now. Yeah, because it fixes that. You can't, by a permutation that fixes a position, you can't change the letter that's there. You can't be wrong. So, because this group already fixes everything that's outside that window, the entire string is respected now. So we got automorphisms of the full string. That is the central insight in this entire algorithm, that we are able to construct. I mean, I struggled literally years to find a way to construct full automorphisms out of local information. I did zillion special cases. And here is the abstraction. This is much simpler than anything I did before in the special cases. Okay? So, this is how we construct global automorphisms out of local information. The next thing then that remains is aggregation of these local certificates. Now, for every t-tuple of my ideal domain, I now have a certificate, either a positive or a negative certificate, and I want to aggregate this information. And I am just going to give a very, very quick sort of hint as to what is being done. If the positive certificates somehow dominate, I'm going to say what that means, then I just look at the group generated by the positive certificate. So I look at all the test sets that are full and look at the corresponding groups. And they generate a group. This is a group that is a subgroup of the automorphism group. If this group extends to a large part of my domain, say more than 10%, then I am very happy because I can use group structure to split my set. Okay, group structure. If it has orbits, I split by orbits. If there is a dominant orbit, then I split by domains of imprimitivity. I'm cheating here. I should be making more remarks, but everybody's hungry now. So tomorrow I am going to give details how this aggregation works, but this is a simple thing that utilizes group structure, but a basic elementary structure of permutation groups. So I will be able to explain this in something like 5 or 6 minutes. In the alternative, if this group doesn't even extend to 10% of the domain, that means that overwhelmingly what we have is the desert where the certificates are negative. Okay? But in that case, if I have negative certificates, what this means is, oops, yeah. Yes. That creates for me a non-trivial theory relation. Okay? So I have a t-tuple in which I know that certain ordered t-tuples cannot move to another ordered t-tuple. Now, there is a little extension needed here. I need to do that not only for one certificate, but in the relation of one certificate and another certificate, because I want to know whether this t-tuple can be carried over to that t-tuple. And in fact, I also need to do it across both inputs. So this t-tuple in the first input, can that go to that t-tuple in the second input? And the same algorithm, almost verbatim, works to do this. But once I have this, then I can just look at one equivalence class of t-tuples, and that's going to be a canonical theory relation. And then I can use the design lemma and the Split-Johnson lemma, so that's the aggregation. Okay. Oh, that was not. Okay. So, thank you. Yes.
When your algorithm runs the speed that you claim it runs, what does it give in the end? Does it land up giving me an isomorphism or a certificate that they are not?
Well, when the entire algorithm ran its course, then it gives me the full set of isomorphisms. If that full set is empty, then they are not isomorphic. If it is full, then I give the entire coset of isomorphisms.
Actually computes all of them.
It computes the entire coset, yes. But that's basically what every graph isomorphism algorithm does. So, I'm sorry?
It doesn't give you a certificate, or how long is a certificate?
Now you are asking about a canonical form, okay? Right? So that's...
How do you prove to me that these two graphs are not isomorphic? Yeah, that's not going to... Yeah, if they are not isomorphic, what is the proof?
Okay. So when they are not isomorphic, the certificate is going to be that the set of isomorphisms is empty. So it is the correctness of the algorithm that certifies this thing. But in practice, the way this is going to be manifested is that I am going to get some canonical thing that doesn't correspond. So along the way, it will just fall out that okay. Right. There will be an obvious moment of rejection of isomorphism. Yeah, but when it rejects, it also produces all isomorphisms. I'm sorry?
You're not proving that it's code T.
No, it's not. No.
The certificate might be called a polynomial.
Certificate.
Certificate that two graphs are not isomorphic. You just have to run through the algorithm again to show that they're not isomorphic.
So at the moment, my certificate is the run of the algorithm. Okay, so. Like if you I don't know, if you use some depth first search algorithm to certify that the graph is connected, well, okay, a tree, but then you have to verify that that's a tree. So in any case, so usually I mean the algorithms simply certify that they do what they are supposed to. So that's quasi-polynomial length. So I have no idea how one could produce Of course, if they are, yeah, so non-isomorphism. No, I mean, but that question stood at exponential at square root of n, the same question. So the shortest certificate we have known was exponential in square root of n long to certify that two graphs are not isomorphic. And so now this is quasi-polynomial.